water that is perfectly safe for you to drink and, perfectly healthy for your maize crop to absorb can actually completely destroy your farm's irrigation system in like a single season. Welcome to this deep dive. Today, our mission is straightforward, but it's absolutely vital. We are looking at how South African farmers and farm managers can prepare their irrigation systems for the realities of drought.
Right.
Specifically, we're going to figure out exactly why drip irrigation lines block and how to stop it using just plain practical science.
Jay, and look, it's arguably the most critical mechanical survival skill for a farm right now.
Oh, absolutely.
You can secure all the water rights in the world, right?
Yeah.
But if that water cannot physically reach the root zone, the crop still fails.
That is the harsh reality. Now, to understand this, we are extracting insights from an incredibly detailed practical article. It's titled Why Drippers Block Sand, Lime, Iron, and Slime. And just a quick note right up front for everyone listening, if you want to dig into this material yourself, you can find this written article living over in the knowledge base on the DWT website. It's really an essential read.
It really is.
Yeah.
It changes your perspective on what clean water actually means in an agricultural context.
Yeah, so let's set the scene here a bit and just think about the sheer mechanics of drip irrigation.
Okay.
Because you're taking the entire water supply of a farm, right? Thousands upon thousands of liters.
Yeah.
And you are forcing it through this labyrinth of lateral lines. And eventually, every single drop has to squeeze through tiny little passages that are well under a millimeter wide.
Wow.
We're talking about passages the size of a pinhead.
Exactly. And that immense volume forced through those, microscopic bottlenecks is exactly why that opening paradox you mentioned is so dangerous.
Yeah.
What is biologically acceptable for the plant can be just mechanically lethal to the pipe. So to understand how crystal clear water kills an irrigation layout, we have to recognize that these emitters die in 3 distinct ways.
Okay, what are the 3 ways?
So they die physically, from suspended sand and silt.
Okay.
They die chemically from limescale and dissolved iron precipitating inside the lines.
Right.
And they die biologically from bacterial slime and algae.
Man, so the hazard classification table for this equipment, it really tells the story of what we're fighting here.
It does.
Because we aren't dealing with, massive boulders or thick mud. We're fighting these trace amounts of material. Let's break down the numbers that take farm water from a minor risk to a severe risk.
Let's do it. Let's start with the physical dirt, right? What we call suspended solids.
Yeah, good.
So if your water has under 50 milligrams per liter of suspended solids, that is considered a minor risk.
50, got it.
But if you push that over 100 milligrams per liter, you cross into severe risk territory.
Wait, just 100 milligrams?
Yep.
Because if you try to visualize that, it's essentially just a tiny pinch of fine dust dissolved in an entire liter of water.
Exactly.
To the naked eye, that water still looks relatively clear.
It does. It looks fine. Then you have to factor in the pH.
Right.
So a pH under 7.0 is a minor risk. But once it creeps over 8.0, it becomes a severe risk.
Okay, why is that? Why the severe jump just from going alkaline?
The reason for this is chemical precipitation. So alkaline water, it acts kind of like a crowded room where dissolved minerals suddenly decide they want to sit down.
Oh, I see.
They drop out of the water and they form this hard scale on the plastic.
Oh.
And then we look at total dissolved solids, or TDS.
The invisible stuff.
Right, the completely invisible mineral load. Under 500 milligrams per liter is minor, but over 2,000 milligrams per liter is severe.
Wow.
And finally, the biology side. If you have over 50,000 bacteria counts per milliliter, you are looking at a severe biological hazard.
50,000 in a milliliter. That is wild.
Yeah.
Looking at those thresholds, it makes me think of a drip system like a human cardiovascular system.
Oh, yeah.
You go to the doctor, you feel completely fine, but they run your blood work and tell you that you have high cholesterol.
Exactly.
It's totally invisible, but it's slowly building plaque in your arteries. These dissolved minerals and trace bacteria in the borehole water, they're silently building plaque in the farm's veins.
That analogy holds up perfectly when you look at the mechanics of a blockage. And, just like high cholesterol, the most deceptive chemical on that hazard table is invisible until the system suffers a heart attack.
Which is?
I'm talking about dissolved iron.
Right. The classic South African borehole problem. The data on iron here is fascinating because Dissolved iron looks completely clear when it pumps out of the underground aquifer, right?
Mm-hmm.
You could hold a glass of it up to the sunlight and it looks like, I don't know, premium bottled spring water.
Because the iron is entirely dissolved in a low oxygen environment underground.
Right.
But the moment that water enters the surface irrigation lines and gets exposed to oxygen, a chemical reaction occurs.
It hits the air.
Jay, it oxidizes. It literally turns into solid rust flakes right there inside the pipe, usually miles away from the pump where you cannot reach it.
That is terrifying.
Yeah.
And the threshold for this causing catastrophic trouble is just staggeringly low.
Oh, it is.
Because the data indicates that clogging trouble starts at just 0.2 milligrams per liter.
Yep.
And anything over 0.5 milligrams per liter is considered completely unusable for drip systems if it's left untreated.
Unusable at just 0.5 milligram per liter.
But wait, I have to push back on this based on the crop guidelines, right?
Okay.
Because the crop tables clearly state that plants are perfectly happy with iron levels up to 5 milligrams per liter.
That's right.
So if the maize actually wants the iron as a micronutrient and the roots can easily handle 10 times the hazard amount, why are we stripping it out of the water?
Right.
Are we literally starving the crop just to save the plastic pipes?
That's the logical question every farm manager eventually asks. Hey, but there is a biological twist that forces our hand here.
Okay, what twist?
We aren't just removing the iron because of the physical rust flakes getting stuck.
Oh.
We're forced to remove it because of something called iron bacteria.
Iron bacteria. What exactly is iron bacteria doing in this environment?
So these are these naturally occurring bacteria that actually feed on the dissolved iron in the water.
Wait, they eat the iron?
They eat the iron, John.
Mm-hmm.
And as they consume it, they multiply and they secrete these complex sugars to anchor themselves to the plastic walls of your pipes.
Oh, gross.
John, it creates this thick, sticky, red-brown jelly called ochre.
Ochre.
John, it's a biological matrix. So this jelly sheets through the lateral lines, and it acts like a glue that captures any passing sand and silt, and it just plugs the emitters wholesale.
So it isn't just dry rust catching in the little holes.
No.
It's a rust-flavored slime monster growing in the dark, and it's acting as a net for everything else.
That is exactly the reality of it. And it's worth noting that dissolved manganese does the exact same thing. It's just a bit slower.
Really?
And it creates a dense black slime instead of a red one. But both will cement a system shut.
Wow. Okay, so if we have clear water pumping out of a borehole that is, secretly loaded with iron, how do we stop this biological glue from forming? We obviously have to intervene before it hits the lines, right?
The golden rule is that the remediation has to happen before the water enters the manifold.
Right.
You must never send dissolved iron down the lines to precipitate in the dark. So the process is a three-step intervention. You oxidize, you settle, and you filter.
Okay, so you essentially force the water to rust on purpose.
You force the rust, ja, but more importantly, you force it to happen in a controlled environment where you can actually physically catch it.
Okay.
So aeration works beautifully for this. You
Yeah.
just spray the water through the air to introduce oxygen.
Just spraying it into the dam or whatever.
Yes, exactly. But the speed of that aeration reaction depends entirely on your water's pH.
Oh.
So if your borehole has a pH of 8, that dissolved iron converts to solid rust in about 30 seconds.
Wow. That is incredibly fast.
Yes, it's very manageable. But if your water is acidic, let's say it has a pH of 6, that exact same aeration process takes days to form rust. Days. And a working farm, well, it does not have days to wait while a crop needs irrigating.
Right, which means a farmer with acidic borehole water, they can't rely on aeration alone.
Yeah.
They would need some form of active chemical intervention to speed up that rusting process.
Joe, they must dose chlorine into the water as an oxidant.
Okay.
And the budget for this reaction is very specific. You need 0.64 milligrams of chlorine for every 1 milligram of iron per liter.
0.64. Right.
And you must inject this upstream of your primary filter so that the newly formed rust flakes are caught in the filter bed, not delivered to the drippers.
So for standard farm scale setups, managing heavy iron volumes sounds incredibly complex. How does a farm actually implement this in one fluid system?
Well, for standard flows, a catalytic media filter is usually the packaged answer.
Okay.
This isn't just a physical sieve. The media inside the filter actually acts as a chemical catalyst to encourage the oxidation process while simultaneously trapping the resulting rust in one go.
Oh, that's clever.
Yeah, it's great. However, if your water is heavily ironed, which means anything over 4 milligrams per liter, the volume of rust will just choke even the best catalytic filters almost immediately.
Yeah, that makes sense. Too much volume.
Right. So in those severe cases, you have to aerate that water into a large settling dam first, let the heavy rust physically drop out to the bottom of the dam, and then pump the cleaner water off the top.
I see. So we've introduced oxygen or chlorine, and we've forced this invisible iron to turn into thousands of microscopic solid rust flakes. But now we have a new problem, don't we?
Ja.
We have thousands of solid particles speeding toward passages the size of a pinhead.
Exactly.
How do we physically catch something that small before it hits the manifold?
Sure.
This brings us to a very specific sizing rule for physical filtration.
Yes, the golden rule of physical filtration.
Let's hear it.
Your filters must remove particles larger than 1/10 of the smallest emitter passage on your entire farm.
Okay, I have to ask for some clarification on the physics here.
Sure.
Why 1/10? Because if the passage in the dripper is, say, 1 millimeter wide, and a grain of sand is 0.5 millimeter wide, shouldn't it just pass right through the hole and out onto the soil?
You would think so.
Why do we need to filter down to 1/10 of the size?
It seems like massive overkill when you just look at the raw measurements.
Yeah.
But it comes down to a mechanical issue called the bridging effect.
The bridging effect.
Yeah, smaller particles don't politely go through the emitter hole one at a time in a single file line.
Right, they all rush it.
Exactly. When the system is pressurized, they rush the exit together, they bridge across the opening. Think of a handful of small, jagged stones. If you throw them into a large funnel all at once, they instantly wedge against each other and block the neck of the funnel entirely, even though any single stone could easily fall through on its own.
That makes perfect sense. They lock together structurally.
Yeah.
So we have to filter out the small stones to stop the traffic jam from ever forming in the first place.
Exactly right. So in practice, avoiding this bridging effect means standard drippers need filtration down to 130 to 100 microns.
Okay.
If you're using clog-sensitive or pressure-compensated drippers, the internal pathways are even more complex, which means you need to filter all the way down to 75 microns.
To put that 75 micron number in perspective for everyone, a standard human hair is roughly 70 microns thick.
Wow.
We are filtering massive volumes of farm water down to the width of a human hair.
It requires serious precision, and choosing the correct tool to achieve that precision is critical, because matching the filter type to the specific water source is half the battle.
Let's run through these filter types based on the problems they actually solve.
Oh.
If a farmer is pulling from a relatively clean borehole,
Yeah.
and they just need to catch a little bit of occasional sand or silt,
Then screen filters are the answer. They're your basic stainless steel or plastic mesh. They're simple and cost-effective.
but if they're pulling from a dam with algae, a basic mesh screen would be a disaster, right? The biological slime would just smear straight across the mesh and blind the filter instantly.
You've hit the nail on the head. Screen filters are totally helpless against biology.
Right.
For mixed loads of dirt, you step up to disc filters.
Okay, how does this work?
So these are a dense stack of grooved plastic rings tightly compressed together, and the water is forced through the microscopic intersections of those grooves. They're a fantastic general-purpose choice.
Wait, if the water is forcing its way through tiny grooved intersections, what happens if the borehole is pumping raw, hard sand?
Ah.
Wouldn't the heavy grit just wedge directly into those plastic grooves and ruin the rings?
It absolutely will. Hard grit destroys disc filters.
Yeah.
Sure. If you are pumping raw sand, you need a totally different physics approach. You need hydrocyclones.
Hydrocyclones.
Yeah.
Sounds intense.
They're great. These are spin separators positioned ahead of everything else that use centrifugal force.
Oh, like a whirlpool.
Yeah, so the water enters at an angle, spinning rapidly. The heavy sand is thrown outward to the walls and drops down into a collection chamber, while the lighter, clean water spirals up and out.
Right, okay.
They're essential for catching heavy grit before it damages your downstream equipment.
And that leaves surface water. If a farm is pumping from a river or a dam carrying a heavy load of algae and organic matter, or if they're trying to catch massive amounts of that oxidized iron we discussed.
Then they need the heavyweights, sand, or media filters.
Oh.
Instead of a single layer of mesh, a media filter uses a deep, volumetric bed of crushed glass or silica sand.
Oh, so it's thick.
Joe. The water has to wind its way through a three-dimensional maze, trapping massive amounts of dirt and slime deep within the bed. It's really the only physical filter that can handle high organic loads without choking instantly.
Now, having the right filter is obviously only part of the equation.
Mm-hmm.
Keeping it clean is where many farms actually lose the plot. The maintenance guidelines are very strict about not just using a calendar.
Absolutely. Backwashing must happen based on pressure difference across the filter.
Which means if I just set a timer to backwash my media filter every Friday, I am managing blindly.
Shall you?
Because if there's a sudden algae bloom in the dam on Tuesday, my filter could be completely suffocated by Wednesday, choking the pump.
Exactly.
Or, conversely, if the water is clean, I could be wasting thousands of liters of water backwashing a perfectly clean filter on Friday. The pressure gauges are essentially the filter telling the farmer exactly when it is struggling to breathe.
That is the perfect way to look at it. As a filter catches dirt, it becomes harder for water to push through it.
Yeah.
That creates a pressure drop. So for screen and disc filters, you must initiate a backwash when you see a pressure difference of 20 to 35 kilopascals between the inlet and the outlet.
20 to 35 kilopascals.
Yeah, but for deep media beds, you wait until the difference hits 70 kilopascals. You listen to the equipment, not the calendar.
Makes total sense. So we've successfully aerated the iron, and we've utilized the correct physical filter to catch the rust and sand down to 1/10 of the emitter size. We have beautiful clear water going into the manifold. But physical filtration cannot stop dissolved limescale from passing through, and it definitely cannot stop microscopic bacteria from slipping by.
No, it can't.
Which means the final battle for the farm survival happens deep inside the lateral lines themselves.
Yeah, physical filtration is really just the first line of defense. To protect the laterals from slime and scale forming inside the pipes, you have to transition to active chemical maintenance.
Let's break down this two-pronged chemical approach, starting with fighting the biology, the slime.
Right. To fight the bacterial biology, you dose chlorine, but it requires precision. You must maintain 1 to 2 milligrams per liter of free chlorine at the far end of the furthest lateral line on the block.
That distinction is absolutely crucial.
Yeah.
Not measuring at the injection pump, but measuring at the very last dripper on the furthest row. Why does the measurement have to happen at the end?
Because chlorine is highly reactive. As it travels down kilometers of pipe, it gets consumed fighting organic matter and bacteria.
Oh, I see. It gets used up.
Exactly. So if you inject 2 milligrams per liter at the pump house, you might have 0 by the time the water reaches the end of the line.
Right.
And if there's 0 chlorine at the end, the bacteria are just thriving down there, building biofilms. You have to check it at the far end using a standard DPD test kit.
For those unfamiliar, a DPD test is essentially a simple color-changing chemical test. Very similar to what you would use to check a swimming pool. If it turns pink at the end of the lateral, it proves the chlorine survived the journey.
Right. And if continuous dosing isn't viable for the farm setup, they can use periodic shock doses of 10 to 20 milligrams per liter.
Oh, a heavy dose.
Jay, you hold it in the lines for an hour or two to just chemically burn out the biofilm.
Okay, so that handles the biological slime. What about the chemical scale? The dissolved lime that wants to precipitate and turn the plastic pipes into concrete.
For lime scale, you use acid.
Acid, okay.
Jay, if your water analysis shows a high scaling potential, remember that alkaline pH we discussed earlier, you use continuous acid dosing to keep the water's pH just below 7.
Okay.
By keeping the environment slightly acidic, the lime remains safely dissolved in the water and passes right through the emitters.
That makes sense.
But if a farm is already suffering from scale buildup, they need to run a remedial acid slug.
What's a slug?
This involves injecting a strong acid solution, holding it static in the lines for about 12 hours to literally dissolve the existing calcium carbonate scale and then flushing it out.
Wow. And this brings us to an absolute non-negotiable safety warning regarding these chemical treatments.
Oh, yes. Very important.
We must stress this heavily. You must never let acid and chlorine meet in a mixing tank or a shared injection point.
Never. The chemical reaction between acid and sodium hypochlorite, or any chlorine source for that matter, it creates lethal chlorine gas instantly.
Lethal gas.
Trace, it is incredibly dangerous. They must be treated as entirely separate maintenance operations on different days.
Wow, okay. There's also a mechanical physics rule when you're doing this chemical remediation.
Right.
Because when a farmer is flushing that dissolved scale and dead slime out of the laterals, they cannot just turn the pump on and let the debris trickle out through the drippers.
No, if you leave the ends closed, you will just clog the drippers from the inside with all the heavy junk you just knocked loose.
Oh man, of course.
Jay, you have to open the ends of the lateral lines completely, and more importantly, you must flush them at a speed of 0.3 meters per second or faster until the water runs absolutely clear.
That velocity of 0.3 meters per second is required because a slow trickle creates laminar flow, right?
Exactly.
The water just glides over the debris.
Yeah.
You need that high velocity to create turbulent flow, a physical sweeping action that aggressively scours the pipe walls clean and carries the heavy rust and dead slime at the open ends.
It's the mechanical sweep completing the chemical breakdown.
So, to summarize these rules of survival we've unpacked today, you have to screen your water analysis against the specific equipment hazard table, not just the crop tolerance table. You must treat dissolved iron before it hits the manifold by oxidizing, settling, and filtering. You have to size your filtration to 1/10 of the smallest emitter passage to prevent the bridging effect.
Yeah.
And you have to keep that free chlorine residual alive at the very end of the line to prove the system belongs to you and not the bacteria.
It is a rigorous maintenance schedule, but it is really the only guaranteed way a drip system survives season after season.
Yeah.
And, connecting all this practical science back to the broader reality of drought brings up a silent threat that many farm managers miss.
What's that?
When a drought sets in, the water table naturally drops.
Right.
And as that water level falls, the borehole pump is forced to pull from deeper within the aquifer. It begins pulling older water that has spent years, sometimes decades, sitting deep in the rock, dissolving higher and higher concentrations of minerals.
So it's pulling a completely different chemical profile.
Precisely. Which means the very act of a drought occurring is quietly, invisibly shifting the farm's baseline water chemistry.
Oh, wow.
A borehole that tested perfectly fine last year, a borehole that was safely in the minor risk category on that hazard table, might silently cross into severe risk territory this season.
Right, because the water table dropped.
Exactly. The iron levels might spike, the pH might drift alkaline, the total dissolved solids will almost certainly concentrate.
Yeah.
And the most dangerous part of this chemical shift is that the water pumping out of the ground will look exactly the same.
Still crystal clear.
It will still look crystal clear. So if a farm manager hasn't tested their water specifically against the equipment hazard table during this drought cycle, they might be looking out at their fields right now, running their pumps, assuming they are saving their crops.
But they're not.
But they might actually be watering them with the very liquid that is slowly, invisibly cementing their farm's lifelines shut.
Man, it is a chilling realization.
It really is.
The water looks the same, but the threat has entirely evolved. Remember, the plaque is completely invisible until the system suffers a mechanical heart attack. Get that drought water tested against the equipment table, filtered to 1/10, and verify your chlorine at the far end. Stay resilient out there, and we will catch you on the next deep dive.